So in this video, we're going to go over rational exponents. So I'm going to introduce you to what is a rational exponent. Okay, so in the past, your exponents have just been integer values, x to the third, x to the negative fourth, but now they're going to be rational values. Rational values means a fraction, okay, with a I'll just write it down, okay, with an integer over an integer. Okay, so that's going to be what we call our rational exponents. And so I need to walk you through that there is, for every radical expression, there's an equivalent rational exponent form. Okay, so if you have the nth root of x to the a, okay, we talked about index before, n is the index. Know that the nth root of x to the a, okay, is the same as the nth root of x raised to the a. However, domain restrictions might play a role. They might change from one expression to the other. But both of these, okay, are going to give you the nth root of the same rational exponent form, which would be x raised to the a over n. Okay, notice a is the exponent on x and n is the index. So the index is the denominator and the a is what was the exponent, okay, on x. So if you have to convert forms, the sixth root of x to the fifth would be the same as x to the 5/6. Okay, the seventh root of y to the third is the same as y to the 3/7. The eighth root of x outside to the third, this would be the same, so to kind of go over this would be the same as x to the 1/8 to the third, right? If I just change this as a rational exponent and now I have to the third, that would give me x to the 3/8, which would be the same as just the eighth root of x to the third, okay? Let's do a few more of these just to introduce the change. So these are equivalent expressions, okay? So every radical form has an equivalent rational exponent form. Every rational exponent can be written as a radical. So a few more. If I had the seventh root of 2x squared y to the third, okay, I have three separate factors here. This is one big product. That would be the same as 2. What's the exponent on 2 in the radicand? 1. So this would be 2 to the 1/7, x to the 2/7, and y to the 3/7. Okay. Notice they each have their own rational exponent. Okay. And we can also think about it the other way. Okay, so if I said what's x to the 7/8, okay, that's the same as the eighth root of x to the 7th. What's y to the 1/3, z to the 2/3? Well, that's going to be the cubed root of y, z squared. So make sure you can go back and forth between the two forms. And the last problem before we start using rational exponents, if you have something like 4x to the 1/2, y to the 1/4, and you just were told to put this in a radical form. Notice they don't have the same denominator, so they don't have the same index. First, 4 is to the first, so that doesn't even need to go in a radical. But you would write as 4 times the square root of x times the fourth root of y. So you can write them as separate radicals. Know that this is one product, okay? So now we're going to go over the fact that because every radical form has an equivalent rational exponent form, which means we can write them as fractional exponents, we can actually simplify our radicals a little bit more than we were able to do in the past. So for example, okay, if we had the fourth root of x squared, we wouldn't be able to simplify that any further. However, if I wrote this in its rational exponent form, I'd have x to the 2/4. And that fraction you can simplify down, okay? Fractional exponents simplify down like regular fractions. So x to the 2/4 is the same as x to the 1/2. Every time you are simplifying an expression, you need to make sure that the rational exponent is now completely simplified, which means you factor out all common factors. So the fourth root of x to the second is the same as x to the 1/2, which means the fourth root of x to the second can actually be simplified down to the square root of x. Now, if you start an expression in radical form and you see how you use rational exponents to simplify it, just make sure your final answer is back in radical form. Okay, so here's one thing we can now do with radicals that we didn't do before. Okay, we simplify the radical as much as we can in terms of if the exponent and the index share a common factor, you can actually divide it out. So you can actually knock down the index of the radical, which you weren't able to do before. And now another thing that you can now do that you weren't able to do before, it's going to be something like this. Okay, this is the problem, the 6th root of x times the 5th root of x squared. Now in the past, you would not have been able to multiply these radicals into the product of one radical because the index is different. And your rule with multiplying radicals is that the index must be the same in order for you to write as the product of one. But if we write each of these with rational exponents, this is x to the 1/6 times x to the 2/5. Well, this now becomes properties of exponents, right? If you think about it, even if it wasn't properties of exponents, okay, I can take this fraction and I can take this fraction and I can write them with equivalent fractions, so I don't change the value, I just make them look different, with a common index. If I multiply the indices together, okay, I get 30. I can get a common index between all of these that I multiply by. So this is going to be 5/30ths, okay? Multiply that, that's going to be 12/30ths. So this is the same as the 30th root of x to the 5th times the 30th root of x to the 12th. That's going to be the 30th root of x to the 17th power. Okay? So you can now, even if it was just 6th root of x times the 5th root of y to the 2nd, you can get this would be, okay, x to the 5/30ths times y to the, we just said 12/30ths, so now you can at least write as the 30th root of x to the 5th, y to the 12th. Okay, so now you can multiply any two radicals together because you now know, okay, you can't multiply them together until they have the same index, but now you know how to get the same index, okay? Using rational exponents allows you to create an equivalent fraction, but with a different denominator so that you have a common denominator, which means you now have a common index. Okay, so this allows you to do different things. So now when you have to multiply two radicals together and they don't have the same index, you now know how to take care of it so that you can multiply all radicals together. Okay. Now we're going to go over evaluating with rational exponent expressions. So the directions will be just to evaluate. So number one, okay, where you have to evaluate, notice the factor, okay, that's raised to the fractional exponent is a constant. Okay, so we need to try and see if we can figure out what 125 to the 2/3 evaluates to be. This is not 125 times 2/3. This is 125 raised to the 2/3. So when you have to evaluate fractional exponents, you need to think about them in their radical form. Okay, so the radical form of 125 to the 2/3 would be the cubed root of 125 to the second. Now, if we do this by hand, okay, I don't know off the top of my head what 125 to the second power is. So instead of looking at it like this, okay, it's a little bit easier to look at it in its equivalent radical form where you can take the exponent and write it on the outside, because I know what the cubed root of 125 is. The cubed root of 125 is 5. And now what's 5 to the second power? 25. So I would write it, when you convert from rational exponent form to radical form, I would write it in this form. Okay, when you convert, write it in that form. So now, number 2, okay, 8 to the 2/3. So if I have to evaluate this, that's going to be the cubed root of 8, and then raise that to the second. It's the same as that. So the cubed root of 8, that's 2. 2 squared is 4. Now I just want to go over a few things with problems that look very similar to this, okay? Number 3. This says, take -8 and raise it to the 2/3. So this would be the cubed root of -8 raised to the second power. The cubed root of -8, can you take the cubed root of a negative number? Yes. The cubed root of -8 is -2. -2 raised to the second power is 4. Number 4. Number 3 and number 4 do not say to do the same thing. Number 4 says you're taking 8, you're raising it to the 2/3, and you're multiplying it by -1. So this is what number 4 looks like in radical form. Okay, so that's going to be negative times 2 squared. The cubed root of 8 is 2. 2 squared is 4, so this is -4. Okay, number 5. 8 to the -2/3. You can have negative fractional exponents. Perfectly fine to have. You can have negative fractional exponents. But the negative must go with the exponent. The index can never be negative. So this will be the cubed root of 8 raised to the -2nd power. So you know how to deal with negative exponents from properties of exponents. The cubed root of 8 is 2. 2 to the -2nd. How do you take care of a negative exponent? Okay, you bring it down. So this will be 1 over 2 squared. 1 over 2 squared is 1/4. Okay, so all problems that look very similar, but be very careful when you are evaluating. So we'll go over a few more so we feel comfortable with evaluating. Number 6, we'll do 1,000 to the 4/3. So we have to take the cubed root of 1,000 and then raise it to the 4th. So the cubed root of 1,000 would be 10. 10 to the 4th would be 10,000. Number 7, -25 raised to the 3/2. That would be the square root of -25 raised to the 3rd power. Is this real? No. So yes, I know we know about imaginary numbers, but what I want you to be writing down here is the fact that you understand that taking a number and raising it to a fractional exponent where the index is even means that what you're going to get is not real. Okay, so one more. We'll do -125 to the 1/3. This says take 125 and raise it to the 1/3 and then multiply it by a negative. The cubed root of 125 is 5. So 5 to the 1st is 5, so this is -5. Okay, so every time that your factor is a constant value raised to a fractional exponent, you need to try and simplify it down and evaluate it. Okay, so now what we're going to get into is actually simplifying expressions where you have constant and variable factors that have rational exponents. Okay, so there's 2 rules we really want to remember when we're talking about simplifying with rational exponents. The first is that you're not completely simplified until you have no fractional exponents in the denominator. Okay, we'll go over that. And, okay, you are not completely simplified until you have no remaining full factors left to simplify. Full factors means like x to the first, okay? A fractional piece, okay, isn't considered a full factor if it's like 2/5. If it's 5/2, then you can break it up to be like 2 1/2. So you technically have 2 full factors of x. Okay, so we're gonna go through this. Okay, this is brand new stuff. Okay, so we're just gonna practice simplifying expressions. Okay, so number 1 would be x to the -3/5. Now, you must also keep in mind all of our rules we already have about our simplified expressions. So one of the rules we have is that we can't have any negative exponents. So what do you do if you have a negative exponent? Okay, you would bring it to the denominator. So this would become, okay, if you had x to the -2, what would you do? This would become 1 over x squared, right? The exponent drops and becomes positive. So this would become 1 over x to the 3/5. But the issue here is, okay, in this problem, we would be done because you can have integer exponents in the denominator. In this problem, we're not done because you can't leave fractional exponents in the denominator of a fraction. And that's because our rule is saying that if I write the equivalent form of this statement, okay, what I really have sitting in my denominator, if I have fractional exponents, is a radical. And you're not allowed to leave a radical in the denominator of a fraction. So if we thought about this in the radical form, okay, we would be multiplying by a clever form of 1 so that the radical was no longer in the denominator and that we had a rational denominator. If this was the 5th root of x to the 3rd, we need to get to the 5th root of x to the 5th in order for this to be simplified. So I would have multiplied by the 5th root of x squared. So if I multiply the denominator by the 5th root of x squared, I need to make sure I multiply my numerator by the 5th root of x squared. Okay, now notice I can't simplify the 5th root of x squared anymore. That's okay. What my real goal is to make sure that that's rational. The 5th root of x to the 5th is now x, which is really x to the 1st. And it's okay that my radical is now in the numerator, it just can't be in the denominator. So my issue here is I can't leave 3/5 in the denominator, okay? So I need to multiply it by a clever form of 1, okay? So that this wouldn't be a fractional exponent anymore. So what you want to do is you want to make sure you get to the smallest integer going up from this fraction. So this is 3/5, okay? So the first fraction I would be at that would turn into an integer would be 5/5. So what must this be? This must be x to the 2/5, okay? So if I multiply the denominator by x to the 2/5, I must multiply the numerator by x to the 2/5. So this is going to give me x to the 2/5 over x to the 5/5. That's going to be x to the 2/5 over just x to the 1st power. Now if you say to yourself, oh, but properties of exponents tells me if I have x over x, I should subtract. Well, if you go to subtract 2/5 minus 1, the exponents, that's going to be -3/5. And you would just be putting yourself in an endless circle because notice that the beginning problem was that you had to simplify x to the -3/5. So the reason, or you know you're done because how much is left of x up here? 2/5. So you don't even have a full factor of x to simplify with this factor of x to the 1st power in the denominator. So this is as simplified as you can get. Okay, let's do another. Number 2, a to the -12/5. Okay, so this isn't simplified because no negative exponent, so we make it positive. So this would become 1 over a to the 12/5. Now what's wrong with this is you can't have fractional exponents in the denominator. So we want to get the denominator to have an integer value. So counting up from 12, what's the first integer we're going to hit? What's the numerator? 15. Okay? So this will be a to the 3/5. You don't want to just get to any random number that would make you an integer here, like 20. Okay, so the reason you wouldn't want to get to 20 here is because this would then be 8/5. And notice, you're now going to put in the numerator full factors of a, okay? You're going to be putting in 1 3/5 factors. You put in too much. This should just be enough, okay? This should always be a number that's less than 1. This exponent should always be less than 1 because this should just be the push so that this became a full integer value. Okay, so it's going to be a to the 3/5 over a to the 15/5. So that's going to be a to the 3/5 over a to the 3rd. So notice, I don't even have one full factor of a. So I can't simplify this expression any further because I don't even have one full factor of a to cancel out with any of these 3 factors of a. But notice, if you had chosen, let's say, 8/5 here, okay, you would have done a to the 8/5 over a to the 4th. 8/5, okay, that's 1 3/5. So you have one full factor of a that you can cancel out, leaving you with a to the 3/5 over a to the 3rd. Okay, one way to make sure that you've completely simplified is just subtract again. 3/5 minus 3 would be the same as 3/5 minus 15 over 5, which is negative 12/5. If that is the issue that you just rectified, you know you're done. If this was not the same as this, that means you could simplify further. Okay? So that's number 2. Number 3, if you have x to the 5/3 over x, okay? So, I have integer exponents only on x, but look at this. 5/3, okay? 5/3 is bigger than 1, which means I have at least one full factor of x. So I should be subtracting these exponents. This is x to the 5/3 minus 1. That's going to be x to the 5/3 minus 3/3. This is x to the 2/3. So this simplifies down to being x to the 2/3. Because technically what I have here is x to the 1 2/3. So I have one full factor of x that I can cancel out, and then I would be left with x to the 2/3. So a problem that's kind of like this. Number 4, if I have x to the 2/5 over x, do I have any full factors of x here? No. Do I have, okay, I have x to the 1st here, so I don't have to worry about rationalizing my denominator, but there's nothing left for you to simplify because I don't have any full factors of x between the numerator and the denominator to cancel out. You can check. Just subtract 2/5 minus 1, which would be 2/5 minus 3/5. Okay, I'm sorry, minus 5/5. That's going to give you negative 3/5. If you had to simplify x to the negative 3/5, that's just going to put you at x to the 2/5 over x once you rationalize that. Okay, so there's nothing for you to simplify here. Now, let's look at a different one. X to the 12/5 over x squared. Is there stuff for you to simplify here? Absolutely. That's bigger than 1, so you know you need to simplify this further. So this is going to be 12/5 minus 2 over 1 would be 10/5. That's going to be 2/5. So this simplifies to be x to the 2/5. Okay. Number 6, what do you do when you have rational exponents like this? Okay, if they're both fractional, don't even think about it, go right to subtracting. Okay, x to the 11 thirds minus 5/6. Okay, so we have to have a common denominator. Common denominator will be 6. So that can stay 5/6. This would become 22 minus 5. Okay, and that's going to become x to the 17/6, so it's positive. So this is just x to the 17/6. All right. That was number 6. Number 7, we'll do x to the 11/7, y to the 12/7 over x squared, y to the 1/2. Okay, so notice, I've got x's over x's and I've got y's over y's. So let's look at our x's first. I see that I have integer exponent in the denominator, that's good, but I have an exponent on x that's larger than 1, which means this needs to be simplified because I have full factors of x in there. So we're going to have to do x to the 11/7 minus 2 over 1, which will be 14/7. So it's going to be x to the negative 3/7. Notice that knocked us down a little bit, okay? And fraction, just subtract them. So that's 12/7 minus 1/2, so that'll be minus 1/2. So our common denominator will be 14. So that's going to be 24/14 minus 7/14. Okay, so that's going to put us at y to the 17/14. So this would become x to the negative 3/7, y to the 17/14. Okay, so now we check, okay. So we now have just x once, y once. This is positive, that's good. This is negative, that's not good. So this becomes y to the 17/14 over x to the 3/7. And now we need to rationalize our denominator because we cannot have a fractional exponent. So counting up from 3/7, we want to get this to be x to the 7/7. So we'll have to multiply that by x to the 4/7. So this is y to the 17/14, x to the 4/7 all over x to the 7/7, which would become y to the 17/14, x to the 4/7 all over x to the 1st. And you actually could have seen that because 11/7 is the same as 1 and 4/7. And notice I could take one full factor of x, okay? This is really x times x to the 4/7 over x squared. I can take away one full factor of x, okay? But don't worry about that, just do the subtracting. Okay, and there's nothing left for us to subtract. This is an integer, and that's an exponent that's less than 1. That's how you know you are done simplifying that part there. Okay, number 8. So number 8, we'll do 16x to the 5/4 y to the 9/2 all over x, y to the 1/2 all raised to the negative 1/2 power. Okay, so let's write that down. I'm going to change my marker, running out of ink. Okay, so we have a product over a product raised to an exponent. So we know the first thing we should do is simplify what's inside. So I have x to the 5/4 over x, so that's going to be x to the 5/4 minus 1, which would be x to the 5/4 minus 4/4. I know I should be simplifying this because this is an exponent that's larger than 1, okay? So this is going to be x to the 1/4, and then y to the 9/2 minus 1/2, fraction, go right into subtracting. That's going to be y to the 8/2, that's the same as y to the 4th, so this actually simplifies to be 16. X to the 1/4, y to the 4th, all raised to the negative 1/2. So now we distribute, that's going to give us, because this is a product, we distribute 16 to the negative 1/2, x to the negative 1/8, because you multiply, and y to the negative 2. So all end up with negative exponents, so this becomes 1 over 16 to the 1/2, x to the 1/8, and y to the 2nd. Now, one of these is a constant factor. 16 to the 1/2 is a constant factor. So you're not trying to rationalize this. Right now, you're checking to see what this becomes. So this would be the square root of 16 raised to the first. The square root of 16 is 4. 4 to the first is just 4. So this becomes 1 over 4 x to the 1/8, y to the 2nd. Can you have an integer exponent in the denominator positive? Yes. Can you have a fractional exponent positive in the denominator? No. So we only need to rationalize so that our x, because the other two are fine. Other two factors are fine. So 1/8, we need to get this to be 8/8. So we would have to multiply by x to the 7/8. Okay? So our final answer is going to be x to the 7/8 over 4y squared x to the first. And now, don't get confused. Oh, I have x over x. Okay, but this is a positive integer now, and this is less than 1. So there's no full factors of x to simplify between the numerator and the denominator. Okay, so let's do one more. Was number 8, I do believe. So the last problem we'll do, number 9, we'll do 8 to the 4/3, x to the 1/2, y to the 6/5 over x to the 1/8, y to the 3rd, times y to the 1/3 over x to the 2nd power. So I have a fraction times a fraction, and each piece of the fraction is a product, so that means I can multiply across. So this is going to be 8 to the 4/3, and now just x to the 1/2, and y times y you should be adding there, so that's 6/5 plus 1/3. So our common denominator should be 15. So 8, that's going to become 18, and that's going to become 5, so this will be y to the 23/15 over x to the 1/8 times x to the 2nd, so we should be adding. So that's going to be x to the 1/8 plus 16/8. That's going to be x to the 17/8. So that's going to be x to the 17/8, y to the 3rd. And so we see, okay, 8 to the 4/3, I need to take care of simplifying that. So what's the cubed root of 8 raised to the 4th power? Cubed root of 8 is 2, 2 to the 4th, so that's 16. So this is 16 x to the 1/2, y to the 23/15 over x to the 17/8, y to the 3rd. So now we check x over x. They're both fractional. So that means I need to subtract them and continue simplifying. So that's going to be, I'm going to do the work right here. That would be x to the 1/2 minus 17/8. So that's going to be x to the 4/8 minus 17/8. So that's going to leave us with x to the negative 13/8. We kind of knew that there would be more left in the denominator because 1/2 is smaller than 17/8. And now let's check out y. Now we know that y has to be simplified. This is an integer exponent, but this is greater than 1. So that means there are factors of y that can cancel out. So 23/15 minus 3. So that's going to be 23/15 minus 45 over 15, right? That's going to give us, 45 over 15. 23 minus 45 is going to give us negative 22 over 15. Okay, you kind of knew that because this is larger than that. So this is now 16x to the negative 13/8, y to the negative 22/15. No negative exponents in your expression, so the x and the y factor have to move down. So that's going to give us, well, this pen is now not working either. So Let's move to a new pen, new marker here. That's going to give us 16 over x to the 13/8, y to the 22/15. Can you have fractional exponents in the denominator? No. So what we have to do now is just rationalize our denominator. What do we want to get this to? If that's 13/8, what's going to be the next integer we can get that to when 13 is now 16 over 8, and when 22 over 15 is 30 over 15. So that means that we have to multiply this by 3/8, x to the 3/8, sorry, and we have to multiply it by y to the 8/15. So what you do to the denominator, you make sure you do to the numerator. Remember, if these numbers are larger than 1, you're picking a value that's too big, and you're going to have to end up simplifying again. So that leaves us with 16 x to the 3/8, y to the 8/15 over this, which becomes 16 x to the 3/8, y to the 8/15 all over x squared, y squared. And you know you're done because this, yes, these are integer exponents, and both of these numbers are now smaller than 1. Okay, so simplifying with rational exponents, a brand new topic, okay? Take your time when you're doing these. These two rules are extremely important that allow you to remember when you are done simplifying your rational exponent expressions.